All right, welcome everybody to our webinar. I am Glauber Costa, a principal architect at ScyllaDB. If you are not familiar with what ScyllaDB is, a quick primer. ScyllaDB is the next generation NoSQL database with automatic tuning features, simpler to use, and ultimately a drop-in replacement for Apache Cassandra, providing 10% of the performance with low and, more importantly, consistent tail latencies. We have open source and enterprise versions, and if you are interested to follow up about that, just drop us a note and talk to us after the webinar. Today, I'm here to answer a very important question. But before I can even frame this question properly, we need to look back in time. Around 10 years ago, we were seeing the rise of NoSQL. You really were seeing this word coming out everywhere, and things like Cassandra, MongoDB, and others. And that happened because of a very, very powerful proposition from NoSQL. Now, organizations big and small could handle massive amounts of data, formerly impossible unless you were in one of the big guys, due to a scale-out architecture. As you need more capacity, you just add more and more and more, and you can handle virtually infinite amounts of data. But the world has changed a lot in the past 10 years. Well, for a change, one quick example of how we did change is that back then, in 2008, security bugs did not have a name and a logo, and now they're on their way to have a dance and a theme song and a movie and something like that. But other things changed as well. Smartphones were not ubiquitous as they are now. Now every one of us carry one of them in your pockets, except for me, because I don't want to be interrupted during the webinar, but otherwise I would. Actually, just 1 year prior to that, in 2007, Apple was just releasing the first version of the iPhone, so we came a long way. Processors are now nothing like they used to be 10 years ago. We found this thing called physics, interesting concept, that this allowed us to keep making processors faster just by increasing their frequency. So we had to try a different strategy, and that was the dawn of the multi-core era. Now, some things never change, and one of the things that didn't change is the necessity to keep scaling out. And Scylla provides that as well. In our QA, we routinely take Scylla to numbers of nodes or like 200 and up to make sure that our users and customers, if you have to handle massive petabytes, exabytes amount of data, you will be able to do so. But commodity hardware looks nothing like it used to 10 years ago. So let's just take a look at a couple of examples. In 2008, Intel was about to release the Intel Core and Core Duo architecture. And what that happened, what that allowed was for us to have 2 cores in a single die. Now, in 2018, the Qualcomm Snapchat that powers the Samsung S8 phone that I carry with me has 8 cores. And again, it's a device that fits in my pocket. So the idea that we will scale out and handle massive amounts of data with commodity hardware is still present, and it's still a cornerstone of what NoSQL is. But what is commodity hardware? It's not the same anymore. And with that, the question that I need to ask today is, given a workload, a data set, some throughput and SLA requirements, would that make sense for us to use a lot of small nodes or a handful of big nodes, as big as they can get? As an example, if I have 200 terabytes of data that my workload needs to handle, should I be using 200 nodes with 4 cores and 1 terabyte each? Or should I maybe be using 20 nodes, 40 cores with 10 terabytes of disk each? And that is the question that we will explore today. There are some natural advantages of using big nodes. Well, if you are in a cloud environment, for instance, bigger nodes have fewer noisy neighbors. And up to a certain size, you are pretty much guaranteed to be the only tenant, meaning you have no neighbors at all. So you don't lose any performance because of that problem. Bigger nodes see economies of scale. And as a matter of fact, we will see one example of that later on in this presentation. It's also usually easier to manage large nodes. Imagine how hard it is to manage a cluster with 1,000 nodes versus a cluster with 10 nodes if you need, for instance, to apply a security update across the cluster. Even if it's automated, it's not that simple. The question then becomes, if those properties are true, why is it that we don't see more and more people using large nodes? We still see like most of deployments trapped into a zone within like between 4 and 8 cores, and sometimes a little bit more than that. But there are nodes available, especially from cloud providers. They're much, much bigger than this. So why is it that people are sometimes not going bigger? And one of the things we hear a lot is, well, I would love to add more and more CPUs to my nodes, but the real problem is that my nodes only have 0.5 terabyte of disk. So I have a lot of data. The reason I don't do bigger nodes is that I still need to handle all that data. And if each node has 0.5 terabyte of disk, what does it matter if I have 100 processors in it? All I'll be doing is increasing the bandwidth gap between those two components. And that is obviously true. But let's take a look at the kind of hardware you can get today at a click of a button. Now, I'll be using, as an example, the i3 family from Amazon. That is, for the Amazon users, the instance class that we recommend for use with Scylla. And let's take a look at the offering. How does it look like? Well, what we have here in this table is pretty much all instance sizes in the i3 family, except for the new and shiny i3 Metal, which we are already testing at ScyllaDB, by the way, which doesn't have a hypervisor at all. But if we look at the current offerings, the CPU count moves from 2 to 4 to 8, all the way up to 64 CPUs. So you can get a CPU, a node, click of a button today, if you are on the cloud with 64 CPUs. Other clouds, like Google, Microsoft, and others, have very similar offerings. But look what happens with memory. That's the interesting part. As we increase our number of CPUs from 2 all the way to 64, memory sizes increase as well, from 15.25 gigabytes of memory all the way to the big one with 0.5 terabyte of memory. Back to our original problem, storage size also increases. We have 0.5 terabyte in the first instance type, but we have almost 16 terabytes, 15 dot something in the last one. And one very interesting thing here happens in the middle. The first 3 instance sizes grow in storage size by adding a bigger disk. Are those disks faster as they get bigger? We can't know, not from the specs. But if you look at the 3 last ones, the 4x large, the 8x large, and the 16x large, your storage space increases by adding more disks. And modern SSDs are incredibly parallel. What that means is that for sure, my storage system is also getting faster, not only bigger. So as we could see here, in the resources in the nodes that we can find in cloud hardware, it's not just the CPU that it's scaling. All resources are scaling proportionally. And of course, if you're not on the cloud and if you're dealing with your own hardware, that's what you should do. You have the freedom to do so, and that's obviously the recommendation. Now, is it more expensive to run bigger nodes? And as we see, it isn't. From 15 cents an hour, we go to 31. So we do have like a 1 cent artifact there, but we get the cent back when we get to the 16x large. So it's not really that it becomes more expensive. At least from the perspective of running things in the cloud, it doesn't truly matter how you organize those resources. The price you're going to pay for them is the same. The second thing we hear a lot is, well, it's all fine. When things are working fine, it might be true the bigger nodes are better. But the real problem that we have to solve with NoSQL is that things fail. My nodes are going to be failing all the time. And when they do fail, I don't want to stream 15 terabytes of data. I would much rather stream only 1, because that's going to be much faster. Now, that makes sense. It rings true. Let's assume it's true. Why not? 15 versus 1, it should be cheaper to stream a single terabyte. So let's call this a fair argument. But failures are much more complex than that. There is also a part of the cost of a failure that is proportional to the amount of failures that you have. And larger nodes, because they do the same thing in fewer nodes, fail a lot less. Just think about it, how many failures you expect in a cluster with 1,000 nodes. At this point, you are having failures every day. And in our example here, if you have a 3-node cluster and each node has 20 terabytes, how many failures you expect versus if you have a 60-node cluster with 1 terabyte of data each. It really is the difference between getting paged to go take a look at that node every week versus once a quarter. And as I said, there is a part of the cost that really is per node. Let's imagine, for instance, that some CPU manufacturers had a bug in speculative execution that forced everybody to, that's of course hypothetical, but that would force everybody to update their kernels in a rush tonight. Even if you automate that, how long does it take to rolling restart a cluster with 60 nodes versus rolling restart a cluster with 3 nodes? So when we look from the failures perspective, it seems like there are arguments, pros and cons. And to break this tie, we need to look at other factors. So let's leave it at this for now and look at other factors. For instance, we need to find the inflection point over which my performance is not getting any better. And why this is important for any software scaling out there? Well, if I double my resources, but my performance only increases 5%, obviously that's not a point where I want to be, or that might be like exactly the point I want to be, but I don't want to go further. So when we talk about scaling and normal operations, so we can unbreak the tie in terms of failures, we need to find that sweet spot. What is the point in which my nodes are getting bigger, but my software stack is not really getting faster? That will be a very natural point for us to put our node sizing. And to do that, I run a benchmark. And the benchmark is very simple. I'm using Cassandra Stress here. If you're not familiar with Cassandra Stress, it will generate, in this case, a write workload, but it's a very flexible tool that can do reads and writes. For the purposes of studying scaling, that will be enough. I have used the default schema, which have 5 columns, each column being 64 bytes. And I will insert 1 billion of those records with quorum writes into a cluster of 3 nodes, I3 X large, replication factor of 3, meaning all nodes in the cluster are basically a replica of each other. And I have a single loader doing this, like a single machine outside of that cluster, pushing that load with 250 threads. So let's see how long does that take. To do that, over the course of the benchmark, I had a latency of an average latency of close to 13 milliseconds, a 95 percentile around 20, a 99 percentile 26, and the 99.9 percentile around 40 milliseconds. Now, when I mentioned earlier that we provide consistent latencies and very predictable, that is one great example of that. But that's not what we're interested at the moment. What really matters is how long did it take me to insert that billion partitions. And that is around 14 hours, 20 minutes. Now, what I'm going to do is double everything. Let's put this here to the left as a data point so we can keep looking at it. And instead of 1 loader, I now have 2. Instead of 1 billion partitions, I now have 2. Each of those loaders writing to a disjoint set of 1 billion partitions each. And my cluster still has 3 nodes, but now the nodes are 2x large with 4 CPUs, and as we saw in the table, all the other resources scaling proportionally. And obviously, because I now have 2 clients, they might finish at slightly different times, and the result I'm going to show you is the one that took the longest. The latency average is pretty close to what we used to do. The 95 percentile is still 21 milliseconds. The 99 percentile around 27, the 99.9 slightly better, still within the error margin, 38 milliseconds. Not surprisingly, the total time it takes to insert this 2 billion partitions is 15 hours, 9 minutes, and the other client finished a little bit faster than this. So all things being equal, I mean, those things are pretty close to each other. This 5% is, again, within a narrow margin that we expect from a benchmark like this. So we can say that at this point, like the 6% difference that we see, it's not really relevant, and those things are pretty much constant. So I double the data set size, I double my resource sizes, and everything stays more or less the same. I'll speed up at this point because I think you got the gist. I'll do the same thing again. I will now have 4 loaders, 4 billion partitions, 4x large is my machine of choice. And what we see here is that we actually get a little better. The average latency is already telling us that, but when we look at the total operation time, it's actually 11 hours, 44 minutes. And that's very easy to explain. As I said in the beginning, there are natural advantages of using nodes that are larger. They will have less noisy neighbors. We can start specializing, which is one of the things we do. Scylla, for instance, will assign some CPUs if the nodes are large enough just to do intra-processing. We will lose some CPU power to actually do background and foreground requests. You will see later how that affects other parts of the load, but we will gain efficiency. Of course, if I have 2 CPUs, I can't just assign one of them to do that. I'm losing 50% of my power. The disks are also at the 4x large family. Now they're coming in instead of getting bigger, I'm just adding more of them. We don't really know why it gets faster in this specific example, but all those things put together, the lesson that we learn is that if your nodes are too small, it's usually not worth it. I mean, you have to have a certain minimum size, and that seems to be around here. Again, this is 22% faster now. So we're spending 22% less time to complete this workload. Let's keep going. When I have 8 billion partitions, I now have 11 hours, 48 minutes, 11 seconds, still within the error margin. And finally, when I get to 16 billion partitions, 12 hours, 30 minutes, 40 seconds, 6% slower than it used to be before. But when we look at this picture from afar, what we say is that the data set is growing every data point. It's doubling every data point, but my execution times are still pretty much constant. So if the database has, like Scylla does, a modern architecture with thread per core, fully sharded, shared nothing architecture, it pays to scale up because we don't really have a point at which we stop scaling, should, of course, your data be well designed. The total data set at this point is 4.8 terabytes. And if you come from the Cassandra world, if you're a person that doesn't have experience with Scylla but has plenty of experience with Cassandra, I know exactly what you're thinking at this point. Well, 5 terabytes, good luck compacting that. I mean, I'll see you next week. And if you don't have this Cassandra experience and don't know what compaction is, a quick primer for you. Both Cassandra and Scylla and other NoSQL databases will accept writes that we will acknowledge from memory when they are in a structure called a mem table, a memory table. In parallel, they go to a commit log to help you in case the node fails. We will ignore that for now. This memory table is every once in a while, given a certain criteria, written to disk in an immutable structure called an SS table. Because it's immutable, as the load keeps coming, I keep writing more and more of those SS tables, and when I need to read from it, it's very slow since I have a lot of tables. And then there's a background process called compaction that picks a bunch of those SS tables, again, given some criteria called the compaction strategy, and compacts them to a fewer number of SS tables. In one example, for instance, I can compact all of the SS tables into one. I don't have to do that. That's one of the possibilities. Compaction has a very interesting trade-off. If I am too fast at my compactions, what tends to happen is that my foreground workload is now destroyed because I'm using all my CPU, my disk, and my resources in general to serve that compaction. If my compaction is too slow, then my reads are going to suffer. And what you have to do in a database like Cassandra that doesn't have autonomous operations and self-tuning is that you need to find those parameters yourself. And they are static and they won't change during the course of the workload. So in this example, for instance, that comes from the Cassandra YAML and also the Scylla YAML, we will read those values, just ignore them. Somebody set the compaction throughput at, in this example, 16 megabytes a second. I can set it higher, as I said, but there is always this trade-off. If I set it too high, my foreground workloads will be destroyed. Now, all of those settings are ignored by Scylla. And what Scylla does is we have a very different approach. We have what we call the I/O scheduler. So the I/O scheduler is a piece of technology that lives inside the database. So we're basically at this point bypassing the operating system, the Linux scheduler. And what we do is when you install Scylla, we will run a benchmark and determine what is the maximum useful disk concurrency. We will never send to disk more requests than that. The requests that we don't send, instead of being queued in the disk, just adding to the latency, because as you can see in the picture, the throughput of the disk, if you get past this point, is not going to get any better. They'll be queued in user space. Of course, the time it takes to process this request is not going to change because we're just moving it from one queue to the other. But as soon as we have those requests queued inside the database, we can start tagging them and prioritizing them. So if I have requests that are marked as compaction requests, regardless of the size of the compaction request queue, when I see a query workload coming in, I can serve that query. And with that, uphold SLA between and among all of those classes. More than that, Scylla is able to look at the size of those queues and using modern algorithms from control theory, determine if this is the correct pace for this process to run or not. This is what we call the controllers. So we automatically determine the rate at which those things should go. By doing this, we don't really need to limit the compaction. And the expectation here is that if compactions are either a CPU or a disk-bound, they are either a CPU or a disk-bound process. They're not like a ghost spirit-bound process. Something physical has to bind compactions. And if I increase all my resources by a factor of 2, my compactions should also be faster. And my Scylla monster just fell. Okay. That's the very most important part of the webinar. Let's take a look at how that happens in practice. What I did is that I used the same cluster that I already had from the previous example. And I'll be calling node2compact. Node2compact does what we call the major compaction. It will pick all of the SS tables that you have in that node and compact into a single one. For the X large, I have circa 300 gigabytes a second. Sorry, not a second, that's 300 gigabytes of my data set. And that takes 1 hour, 45 minutes. When I move to the 2X large, node2compact to compact this entire data set takes 2 minutes more, so basically nothing. 4X large takes a little bit more. As we saw, like in the previous example, as I start specializing and assigning cores, I will take more time to do some of those processes. That's usually not a problem because in reality, all those things are happening at the same time. I don't have something that is just using the network versus just using the disk. And even then, the difference is not that large. Given, again, let's not forget that from one point to the other, I am doubling my data set size. For 8X large, I have 2.4 terabytes, and I'm still compacting this in around 2 hours. And for 16X large, I have 4.8 terabytes, and the total time to compact this node is still 2 hours and 11 minutes, about the same. So what we can see is that, as expected, because we don't have to artificially limit the compaction speed, I can basically compact the entire data set in the same time. So long as the resources are scaling proportionally, having larger nodes is also not a problem from this perspective. Well, we need to talk about failures again. That's how we got started. And the claim that I have to make is that a lot of people think they care about the time it takes to restore a node, but in reality, you shouldn't care. Why shouldn't you care? Because the reason people care about the time it takes to restore a node is that the performance of your database while you were doing this, it's horrible. So you want this to end as fast as possible. You're streaming data, you're moving data around, your SLAs are basically destroyed. But what if they weren't? And things like the I/O scheduler can also help with that, because now my streaming reads, my streaming writes, and things related to the streaming of data from one node to the other are also going through those schedulers. But we have more than that. we have features like heat-weighted load balancing, specialized to handle the case of restarts, failures, and whatnot. And what happens with this feature is that when a replica goes down and comes back up, we are assuming in this case we're not losing data. Think a rolling restart, for instance, to handle hypothetical CPU bug. My caches are cold. And what happens when my caches are cold is that if I send a lot of requests, a lot of read requests to that replica, they're going to take a long time to return, and I don't want that. But on the other hand, if I never send requests to that node, my caches are never going to get hot in the first place, and I'll never get out of that state. So what we come up with is heat-weighted load balancing. We have, you don't have to worry about the formula. It's basically a mathematical relationship that tries to optimize those things. I have, as a function of the hit rate of the node, which is the H in the formula, I decide what is the proportion of the requests that I optimally send to one of those nodes. That is a feature that we introduced in Scylla 2.0. You can see here in the picture that before that feature existed, the restart of the node is visible in the cluster. Again, because the requests coming back from that replica are now a lot slower. If I look at, let's see how it works under the hood, I can see the yellow node just restarted and their cache misses are too high because the caches are cold. But as time goes by, they're deterministically goes down. An inverse thing happens with the number of reads they're sending to the other replicas. As time goes by, I am sending less and less of a proportion of the reads to the nodes that were still up and more reads to the node that just went back. And the effect of latency is that before heat-weighted load balance was present, I have a workload here, a read workload that is serving reads at the single-digit millisecond. When that node restarts, my 99 percentiles go all the way up to the hundreds of milliseconds, and you can see that it's a little bit shaky until, again, the caches are warm. But if I am using heat-weighted load balancing, I have very few peaks, and they're also much smaller. So you can see here before, you can clearly see the restart, but after we're using heat-weighted load balance, the peaks are in the tens of milliseconds instead of the hundreds, and I barely see them. Again, the result is what you see in the picture. You basically cannot tell, aside from a very small glitch, when that restart happened. The conclusion for today's webinar is that Scylla scales linearly in the amount of resources. So when everything is fine, as the more resources I add, the more performance that I get. This scalability is not only something that affects your ingestion and your reads, it also affects background process like compactions. We also saw that during failures, even if it takes longer to restore the node, specialized features like heat-weighted load balance, together with generic features like the IO scheduler and the upcoming CPU scheduler, will help you keep your SLAs. So the time it takes for that failure to go away doesn't truly matter. But when I was preparing the webinar and I was almost done with the slides, I reached this point and I said, we've been assuming that it's going to take more time for the node to recover. As we said in the beginning, I mean, it's obvious. It takes 4 hours. If I have 5 terabytes and if I have 1 terabyte, of course it's going to take more to stream those 5 terabytes. But is it true? We saw in the compaction example, for instance, that I could compact a data set that gets larger in basically the same amount of time because all the resources that I have in the machine are also getting more powerful. Why wouldn't that be true for streaming? We have to question that. And that's what we did. If I look at streaming in a database like Apache Cassandra, for instance, I can see the same setting, the same manual setting that I had with compactions. I have to set a maximum, I had to set a point, because if I don't do, I will destroy my foreground workload. Those things are not network bound. If I look at the i3 16x large that we used as an example, the largest machine that we have used, it has a 25 gigabit network link. If the network was the bottleneck, I could transfer that in less than half an hour. I don't see people reporting those results out there. So we're pretty much sure that streaming data from one node to the other is not really a network-bound process. And if it's not limited by the physical link, and if it's not limited by an artificial limitation like we have here in this example, 200 megabits a second, then shouldn't we see the same thing that we saw with compactions? So what I did is that I had those clusters that were still there, and I got the node that I called node 2 compact at, and I destroyed it. I just got rid of all the data. And I joined that node back into the cluster with node 2 rebuild, if you're curious about that. And what this is going to do is it's going to rebuild that node from the other two. Let's look at what happened. That happened. The time it takes to rebuild a node, if your resources are scaling together with your data set, is about the same. And it doesn't matter the size of the data set in that case. We have to revise this conclusion. What we thought this whole time is not true. And my revised conclusion is that Scylla scales linearly in the amount of resources, and if your software can do that, you basically shouldn't worry about getting a sweet spot. You go as big as you want. The linear scalability also reflects on background things like compaction as we saw streaming. During recovery, your SLA is going to be kept, even if it will be true that it would take longer to recover a node. But as we just saw, that isn't true. It is a myth that we would love to bust. And that's what I had for today. Keep in touch, and I'll be more than happy to take some questions now. As Matt said, you were already allowed to put your questions. I do see that I have some here in the Q&A. Okay. So I have a question here. I think I should click answer live first. Is RAID 0 still preferred when one will run much larger nodes? Okay, so you should see that I'm answering this live. So basically, that's up to you. If you're talking about RAID versus other technologies like LVM and etc., that is basically a choice. If you're talking between RAID 0 and RAID 1, for instance, and other levels of RAID, RAID 0 is still preferred. And the reason is exactly as we saw. If I lose a node, then I have to basically rebuild this node from another node. It won't take more time because all of the other resources are scaling at the same proportion. So we have other replicas, just do RAID 0. That's what we do by default in our Scylla setup scripts. And you shouldn't have, you shouldn't have any of those trade-offs. Okay, so I have another question here. I understand what you say about the I/O scheduling providing SLAs, but what if my workload is CPU bound? That's a great question. I'll mark here as answered. And well, so for a long time we had the I/O scheduler within Scylla. The I/O scheduler, what it would do is it would look at workloads that we would assume to be disk bound, because that's the reality until at least 2 years ago. Most databases would be CPU bound, and even if the workload doesn't, most workloads will be disk bound. Even if your workload is a little bit different, at some point you will saturate the disk. Your requests that are pending will go to sleep, and I kind of control the CPU with that as well. But what we're seeing now is that those very i3 machines, they have NVMe disks that can crunk up to 10 gigabytes a second, which is incredibly fast. We have a lot of loads that are not disk bound anymore. And because of that, Scylla is actually about to have a CPU scheduler. Some users are already using a partial version of the CPU scheduler in Scylla 2.0, and we're having more and more code hoping to have the final version real soon. Okay, so I have another question here. What are the caches that were mentioned in heat-weighted load balancing? I'll answer it live. And well, Scylla comes, that's something that, because I'm not doing an architectural tour of Scylla, I didn't have time to explain. But Scylla comes with an embedded cache. We are basically never using the operating system page cache, and we assign all the memory for ourselves, and we have the Scylla unified cache instead. So you don't have to worry about tuning how much memory goes to page cache, how much memory goes to row cache, key cache, etc. All the memory is used to the unified Scylla cache, and that holds everything, including, of course, your data. So when the node gets restarted, or something happens with the node, those caches are of course code, and with hit weighted load balance, I'll be able to manage that. So okay, and I'm done. So let's wait a bit if you have more questions. Okay, so some people apparently sent questions through the chat. Yeah. All right, so I'll just read them from the chat, but I'm not sure if that's going to change anything in the dynamic of the webinar. But we have a question here. Now it's scrolling. Let me get that to focus again. I assume all your tests are done with ScyllaDB. Have you done similar tests with Cassandra? So we had, of course, and Cassandra is a technology that is in the market for a long time. And we do know, for instance, that because of the JVM and other architectural decisions that the Cassandra project takes, Cassandra doesn't scale that well. So obviously, the whole part about scaling that I talked about, I emphasized that the software stack is very important in that case. If your architecture is different, of course, you're not going to have the same results. So the way to make the statement generic is you should test. The first thing you should do is you should test your software stack to see where those balances lie. In the case of ScyllaDB and all what we call like modern architectures, we are, for example, fully lockless. We never ever take a lock in the CPU. Again, due to our architecture, you can keep scaling linearly. Other software stacks will be different. So, okay, what is the average time it takes to displace Cassandra with your solution? I would say that depends largely on you. So I'm hoping not that long. But ultimately, I mean, if you're not using Scylla yet, give us a note, drop us a note. We get in touch and maybe run a POC. All right, so I think those are the questions that I had for today. And Matt, do we have any finishing procedures that we got to take?
I don't believe so at this point. If we feel like everything is done inside of the webinar, Julia, if you're ready to do that, and Glauber, if you're ready to be concluded here, we could go ahead and end that webinar. Again, I'll just wait for Julia as the host to have that control to do so. But other than that, if there's any other communications or anything that, it looks like we had another, we had the question that we just answered pop into the Q&A. Thank you very much, Alain. But if there's anything else that we need as far as follow-up contact, you see the information here on the screen. Please do reach out to everybody at Scylla, and I'm sure that they'll be happy to get back in touch with you and address any questions or needs that you may have.
All right, thank you.